Can also someone tell me if they're able to listen to me on Teams? Just want to make sure. I will take that as a yes. Okay, cool. Okay, thanks. Um, so yeah, today we are discussing triplane representation, and usually up till now, people have been using a 2D spatial representation or a 3D volumetric representation of any input data. But lately, there have been a fad of another representation called as a triplane representation. We'll discuss more about it. But okay. But first, volumetric representation. You have an image or you have an MRI scan, which is 3D. So you are technically storing it in a 3D voxel grid. And it's quite precise because for each XYZ coordinate, you have explicit value at that location. But if you go till 512 cube or even 1024 cube resolution, it will take up a lot of memory, and then it will be difficult for further deep learning pipelines as well to process it. So it's memory expensive as resolution increases. So people want to shift from volumetric representation to something lightweight and yet almost equally fast. So here comes neural radiance field. We'll discuss about this particular technique and then we'll go into triplane representation. And once we discuss what exactly it is, I'll try to explain in different contexts it is being used and maybe try to connect with some of our work, which is related to biomechanical modeling or for mind surface generation of the brain. So neural radiance field nerves are nothing but you have some images from a particular camera point. You have from different camera angles, you have some images, and using that, you want to construct a 3D model out of it. And how do you do that? You have an image, you take up any XYZ coordinate, you pass through a ray. Imagine that you have actually defined this grid on -1 to 1 cube. You have an image, and at any particular point, you throw a ray. That ray, how do you define a ray? A ray is nothing but at each point, XYZ coordinate, but an angle with the vertical and the horizontal, which is theta and phi. So when I say throw a ray from a particular point, I mean give me XYZ coordinate and a theta and a phi. So you pass this ray, it goes inside the cube. What does it mean by going inside the cube? Is nothing but you're sampling XYZ coordinate. Again, this is x2, y2, and z2. This is x3, y3, z3. But because it's in the same ray, it has the same angle. So the theta and phi that we define is still the same. Daniel, can you close it? So you get XYZ coordinate. You send this to a multi-layer perceptron, and you ask the multi-layer perceptron to tell me at any particular XYZ coordinate, what is the color of the 3D object. Imagine there is a random 3D object that we are trying to learn, random initialize, something like that. You want to know at any XYZ coordinate, what is the color, and if there is any density on that. What is density? Is there even an object over there? If there is an object, this density value will increase. If there is no object, this density value will be 0. So you do that for each of the points on this image. You sample XYZ coordinate at a lot of rays. At any ray, you sample, say, like 100 points, 100 XYZ coordinates, but with same theta and phi. You send it to a multi-layer perceptron. You try to learn RGB, what is the color at that point, and the sigma value, which is the density. But what you'll notice is that, for example, this is ray 1, and let's go into this ray. This is ray 1. You sample a point XYZ coordinate, and you have density 0, more or less. As you go further, the density is still 0. But as you enter into the object, the density increases. So this means that there is an object at this particular XYZ coordinate. It is starting from here, but as you go further, the object is still there. The object is still there. The object is still there, but it goes down. Now there is no object. So you have actually defined the starting point and the ending point using that ray of the object. So you calculate this for a lot of rays on this image and also on every image that you have from every camera angle. Once you have that, you have the RGB value at any particular point because that's what your multi-layer perceptron is predicting. And using the RGB and the sigma, whether there is an object or not, you use a weighted average of all of these points and you calculate the pixel value over here. What is pixel value? Nothing but a color. So essentially, you pass a ray, you sample a lot of points, you predict XYZ, you predict the RGB value at each point, you get sigma value at each point, you take the weighted average of all of these values, and you predict the pixel value over here. And because you already have the training set, you already have the ground truth pixel value. So you just take you just take MSE loss, and you back propagate again and again and again with lot of rays, with lot of if you have a lot of images from different camera angles, or it can work till using 4 images as well at the bare minimum from each of the 4 sides. So essentially, using 2D images, you're constructing a 3D model out of it by using a multi-layer perceptron. But now you need to know that this whole knowledge of the 3D object is in the multi-layer perceptron. There is nothing else. You are essentially saying that give me the RGB value at any XYZ coordinate. So the whole information of the scene is with the multi-layer perceptron, and that is why it is called as implicit representation, because you're not explicitly storing values like voxels. You're just using a multi-layer perceptron. You can just sample at any XYZ coordinate and you'll get a RGB value, and you can create a whole volume. And you can render multiple views from that, like basic computer vision tools are there that given a volume, you can render then an image from this particular angle as well. And this multi-layer perceptron, you overfit on each of the object. And it takes about 1 to 2 days. So it's pretty time consuming. But once you do that, this multi-layer perceptron have all the information that is there for the 3D object. And the good thing is that usually a scene which can cost you 15 GB of memory, the MLP will use only 5 megabytes, and then you can get the whole object from every angle. So it's very memory efficient, but it's expensive because for predicting each point, if you want to render an image, for predicting each point, each pixel, you have to throw array, you have to calculate so many points, you have to average them out, and then you'll calculate the RGB, the color of the image. So this means that a lot of iterations, a lot of forward passes, computationally a bit expensive. But at the end of the day, the key takeaway that we want to take from this is that a whole multi-layer perceptron can actually represent the whole scene at a lower memory consumption, and based on positional input, it can output a color. So a multi-layer perceptron can incorporate all the information for any scene or any object. So this is nerves, and this is the building block of how the intuition of triplane representation came into being. And we'll now talk about that actual thing, triplane. So nerves, as we discussed, that a multi-layer perceptron, which when you enter a position and a direction, this is XYZ. We are not going into detail of that, but at the end of the day, position, direction, a big multi-layer perceptron get the density and the color. And in voxels, you will store explicitly each value. Now people thought that why don't we have a trade-off between these two? This representation have a spatial bias because it's spatially structured. So you have XYZ coordinate in the structure itself. So I want to get some planes, and I will arrange this in orthogonal fashion such that I can sample any position. I sample any position in a volumetric representation. This is XYZ coordinate. But now, instead of getting explicit value from here, I'll just take the feature that I get when I project this position XYZ onto this plane. I get a value over here, I get a value of from here, and I get a value from here. You'll pass this into a smaller multi-layer perceptron and get the density and color. So it's a trade-off, getting the spatial representation from volumetric, but also using the implicit representation, that is using multi-layer perceptron to actually calculate the value of interest and at any position X, Y, Z. So it's a mixture of both implicit and explicit, and that is why it is called as hybrid, which is explicit from volume and implicit from nerve. So this is essentially triplane representation. Now the question is, how do you actually get these triplanes? You process some images, you process some volumes, and you use an encoder, you output 3 planes. And one thing, that this plane looks like a single channel, but actually it's not. Each of these plane has a thickness, let's call it 64 channels. So while it is being represented as one single plane, but actually it has a thickness of 64, which is nothing but 64 channels. So when you have a position, you project this onto this plane. So you are actually getting a 64-dimensional vector out of it. You get a 64-dimensional vector, you get a 64-dimensional vector, you get a 64-dimensional vector, you concatenate or add them, send it to an MLP, and get the density and color. So this is essentially everything about triplane representation, as to it is a trade-off between explicit and implicit, and it performs better than both of them. So now we'll just look into how we get these triplane representation and in what ways, what people have tried to model using this representation. So how to get this triplanes? Standard StyleGAN architecture over here. I will not go into detail as to what this paper do exactly, but we'll focus on how they get the triplanes. Standard StyleGAN, again, a latent representation, random vector generated from a normal distribution. You send it into a multi-layer perceptron, but you now condition it on some camera parameters because you want to model the 3D object or you want to render an image from a particular angle. So just imagine just 25 scalars. You just condition using these scalars, this multi-layer perceptron, get another vector, and you convert this vector into a whole 2D representation. This is nothing but convolutions, simple convolutions. So you have a vector input, you try to convert it into some planes. It has some channels. It's 250, it's 96. You just divide these channels into 3 parts, and you get each of the plane of 32 channel, and you just arrange it like this. And now, if you just sample any XYZ position, you'll get some vectors, which is 32 dimensional here. You'll get 3 vectors because you're projecting it on each of the plane over here and over here and over here. You'll get 3 vectors, add it or concatenate it, send it to a triplane decoder, which is nothing but MLP, just like nerves. You sample point from in the nerves and you send it to a multi-layer perceptron to calculate color and density. In short, vector, convolutions, get planes, and send it to a multi-layer perceptron, and you try to model color and density. And this is volume rendering. This is basic computer graphic differentiable rendering tools that you can use, that when you enter XYZ coordinate, colors, and some camera parameters, it can render an image from that particular angle. And then this is just trying to do to train this triplane representation. But again, we'll not focus over here. We are focusing on how you get this triplane representations. And if you want to make a generative model out of triplane representation, you use like what they do in StyleGAN, latent representation, get the planes, arrange it in an orthogonal fashion, sample points, send it to a multi-layer perceptron, and get color and density. So this is how you get triplane representation if you want to make a generative model from noise. But you can model a lot of other things. ignore the top layer right now. Let's focus on the bottom one. I said that you have a normal distribution. You sample a vector, you send it to a multi-layer perceptron again. It's another vector. You do convolution just like before. You get some planes. But now each of the XYZ coordinate, earlier we were trying to learn color and density, but now I'll learn texture, that at any particular X point, what is the text, what should be the texture of the 3D image. That texture can be color, that texture can be like materialistic property, anything. So now you have got a spatial representation. You can choose whatever this point should represent. Over here is texture. So you're modeling texture using triplane representation. And if you want to model some geometric aspect of the model of the object, then you again sample a latent vector. You pass it to a multi-layer perceptron. Again, go to the convolutions, get the planes, reshape it again, and you sample the point. But this time, this one will model the deformation of any 3D point. It can be, essentially, I'm saying that you have a grid, you have some XYZ coordinate over here, and you want to know how much this point I should move in order to make this grid into a 3D mesh of any object. So I'm saying that each of the point will now tell you how much the point at this particular XYZ should move. And because should move is XYZ, so you're getting deformation in X direction, Y direction, and Z direction. You will input this point, you'll input this feature, send it to a multi-layer perceptron, and get XYZ deformation. And you will model the deformation from a latent vector. So this is how you can generate meshes as well from a random vector and deform any template. And for any template, which points, XYZ points over here, how much it should move, you'll sample the points, you send it to a multi-layer perceptron and let him do the work. So this is how you model the texture and deformations. And up till now, we were talking about the input is actually just a single vector. But what if I want to auto-encode? So you have a 3D model, which like a 3D mesh or a point cloud. You can do a 3D convolution. You'll again output a volume out of it. Why don't you just average at each of the axes? You'll get 3 planes and just arrange it. Again, you got a 3D a spatial representation. You'll sample some points and you send it to a multi-layer perceptron to calculate anything that you want. Over here is the SDF value, that how much is this point actually far away from the actual boundary of the 3D object. So SDF, sign distance function. And you're modeling the texture as well, because this is textured. So you can model that as well. So this is about, again, modeling SDFs now and texture. So we now know how to model deformations. We now know how to model the SDF of any point. And we now know we can model the texture. But once you have this, and this is not a generative model, right? And people now have been using, you cannot do diffusion on 3D volume because it's memory intensive and computationally expensive as well. So now you can do diffusion on these representations. At the end of the day, all you want is you want a noise. It will try to generate one plane. You get another noise, get another plane, get another noise, get another plane, arrange it, and then you can reconstruct any model. So we'll talk over here. Again, we'll model deformation. And I said that you can directly model a diffusion process on the triplane representations. So over here, what I'm trying to do is I just randomly initialize the plane. I explicitly define that each plane will be 32 channel, 64 cross 64. I just arrange it like this. I sample the points, and I want to calculate how much to deform this point. And forget about neural ODE right now. we'll have to go into detail how that works. But at the end of the day, you can actually model the whole triplane representation from noise. You can learn this triplane representation directly from noise by constraining each of the points, XYZ coordinate, how much it should move. You add some losses to it, and you model the whole triplane representation for any point, for any object. And in this way, this is generative. Now you have multiple triplanes, like you have 100 objects. You try to learn 100 triplane representations of those 100 objects. Now you have the data set of triplane representation. Why don't you just concatenate it all together and do a diffusion like normal? But over here, the good thing is that you will be doing 2D diffusion rather than 3D diffusion, because uh, like all of the planes are 2D. It's just that you have increased the channels in the 2D representation. But why this is useful is you have reduced diffusion from 3D, and now you're doing it on 2D. You're now using 2D diffusion and latent 2D diffusion. So now you can model, now you can sample, once this is trained from the noise, you can sample any triplane and then rearrange it, sample the points at each of the points, and you have already trained a multi-layer perceptron to calculate how much it should move. So XYZ coordinate, you have a new triplane representation, sample the point, put it into multi-layer perceptron, get how much it should move, and create a mesh. So again, the key takeaway is you can use diffusion on this triplane representation as well. But now we have been doing diffusion from latent vector. We try to construct a triplane representation. From that triplane, we try to do diffusion. But now, obviously, diffusion transformer is on the rise. So people did that as well. And this is ICLR 24 this year. Essentially saying, we'll just look at this figure, that if you have learned 3 triplanes using any method, for example, this method or any method, you have learned the triplanes, just pacify it and send it to a transformer. At the end of the day, all you want is a generative model, and what you can do it by diffusion, or just like imagine these are just simple images, patch it and send it to a transformer, and it will do the self-attention at each of the points, and it will also model interaction between these 3 triplanes as well. So the idea is you apply the transformer attention on individually on each of the triplane by patchifying it, but also have attention between these triplanes. And then you train the transformer, and then you can sample it. You can sample the patches to construct these triplanes. And once you have, again, the triplane, you'll sample the points. Again, you send it to a triplane decoder, which is nothing but an MLP, which you have trained already, and you'll get a mesh. Now the thing is, the triplane representation, you can do diffusion, you can do transformer, but how is it valuable to us now? I ran some couple of experiments, and it's still tricky to model the brain, but I still have some hope that it will work. And what I was doing was I was modeling from a template, and at any XYZ position, how much I should move the brain template, and deform the template into the required brain cortical folds, given an age or given an input MRI scan. You can condition it something, but you can use the deformations using this triplane to deform the template and form a brain. So that's one thing. And this particular paper, has actually done it on pancreas, actually, that they deform a template pancreas and a template pancreas to a subject-specific pancreas. And what if the input is a point cloud? So up till now, input was volumes, input was 2D images that you can construct triplanes from, and inputs were latent, a random vector. But now what if the input is a point cloud? And again, at the end of the day, the aim is just get a three planes which you can sample from. So what people have done is you have a point cloud, and each point cloud is nothing but a point XYZ coordinate and maybe some features, depending upon your domain. You just input, you just put this features of each of the point from a into a multi-layer perceptron and get another 20, let's say 256 dimensional vector. So you get these points again. It has the same XYZ position, but now the feature vector has increased from 3 or to 256. But now you just project them on this plane. If you project them on this plane, and you'll get another 2D plane from this. And when I say project, I mean this is XYZ. Just bring it down. It will correspond to this point. But what will be the feature vector of this point? Exactly the value of this feature. But if multiple points are coming into the vicinity of this point, you just average them all together. So again, you have just points in the space. You just project them into one of the plane, and you have a like XY plane now. But you can do this on YZ and ZY as well. So if you have three planes like that, you have come to the same spatial representation that is nothing but triplane representation. And you can sample some points and do some stuff with that. Or you can just simply use these planes and just send it to a 2D unit and model something else as well. At the end of the day, the point is points projected, get a triplane. Now either you process this triplane itself to do something, or you take this points, which is over here, and you try to, I forgot about in this paper, point. Okay, yeah. So you get these plane features, you concatenate them together and send it to, and you are just processing the triplanes now itself. You send it to a VAE autoencoder, nothing, just simple unit, another vector, simple VAE strategy. But now you'll just say that, look, once I input the triplanes, latent representation, I output the triplanes, I'll again reconstruct it into orthogonal fashion, and I'll just sample the points and I'll say XYZ coordinate, give me the SDF value there. But again, the key point is point cloud converted into triplanes, Now you can use it into a VAE, or you can use it into diffusion, or you can use it into a transformer. We'll not go into detail of this. It's quite convoluted, but yeah. So you have triplane representation, and you can model in whichever way that you want. And the good thing is that it has a spatial structure, so you don't have to go into explicit volume metric representation, but yet it is fast because you're using a very small multi-layer perceptron to sample and get the actual value of interest at any XYZ position. So you train it like this. And again, now if you have this triplane representation, and if you've got a latent vector over it, do a simple diffusion on that. At the end of the day, all you want is how to generate this triplane representation. Process it, you have a latent vector, do a simple diffusion. If you have done the diffusion, you can sample the triplanes. Once you have sampled the triplanes, you have already trained this MLP. You can just sample the points, send it to this MLP, get the whole object out of it. That's pretty much it. But one thing, talking about biomechanical models, I mean, I don't have a very complete knowledge of how biomechanical models work, but if I were to think about to use it, at the end of the day, this is nothing but if you want to handle a point-wise property of the object, which can be texture or color, but can be related to some biomechanical constraints as well, that look, the points or a cluster of points at a particular location should follow this loss function. So you can just sample the positions, get some value out of it, and put a loss on that. So if you have anything, like when will you think about triplane? If you have a spatial representation and you want to put constraints on those spatial representation, that how those points should be constrained or should work or should then this representation is one way because it gives you a spatial context to it.
Are you can saying that you can have a regionally specific loss?
You can, because you are in control of sampling the points. So if you are having control of the points of, like you're sampling over here, you know XYZ coordinate. And if you know that this particular point should follow this loss at least, or there should be some relation of XYZ like this, then you can actually enforce this over here. But earlier what you would do was there was a volumetric representation, it's heavy, you cannot use that. But this is giving you a lighter way to do it. So you would normalize, you'll put a Laplacian loss on some cluster of points, or you'll say that each point should not vary significantly from the nearby points. You can do the same, but in a lightweight fashion. And this is faster to train, and it has shown better modeling capacity as well. And if you want to make it generative, obviously, you can now do diffusion and transformer and BAE, anything that you want. So that is why I feel this is quite versatile, and lately what people have been doing is how to model the interaction between these three triplanes. That's it. That is the sole research question that they are handling. And over here, they do that by simply patchifying and do the attention. Simple. You patchify each of it, send this for simple. This is simple transformer attention layer. But now, if you want to model all three if you model context between all three, you send it as well, do attention, and then you do cross attention. So basically, cross attention between the whole thing versus and a patch. So people have been trying to do how to model a relation between these three planes. So, and there are multiple other ways as well. But yeah, if you have three planes, you can constrain the points because you have control of sampling. It's lightweight, and you can make it generative as well. This one? Yeah. This is nothing but you have the patch, right? You just flatten it. So this is nothing but these patches lined all together. This thing. This whole. What's the difference between the input on the left and on the right? This is for all three planes, and this is only for one plane. This is fxy. So if you concatenate the three inputs here, you get the same thing? Yes. Okay. But now what you're doing is get the attention between all three and xy, all three and yz, all three and xz, right? So yeah, so yeah. I have a question on the first side. So if I understood correctly, like you have one nerve model per object. Yes. You overfit and it takes 1 to 2 days. I mean, again, this is 20. One object, like yeah. It's one scene, like can be one object as well. But yeah, it's one scene. So if I'm modeling this room, I'm going to take 1 to 2 days to model this room. And now you can ask me to recreate 3D object of any particular point in this room. Yeah, I can interact. I don't know, like from like a computer vision point of view, you can't add in something else. Yes. So like, people have made it fast. This is like the first version of Nerve. There has come a lot of improvement, but this one takes 1 to 2 days. The very first one. One scene. One scene, yes, one 3D scene. Because you are actually overfitting this multi-layer perceptron using these images for 1 to 2 days. Okay. I mean, maybe you said it already, but isn't it a way to add like an extra like confounding like parameters to say, okay, I want all the objects in my scene to be like green, something like that. Something stupid, but add a constraint into the model to parameterize it a bit more. Or well, you are not editing the object over here. The aim is
Yeah,
not editing.
exactly. That
Yeah.
would be existing. Yeah,
Yeah.
it's not possible.
The aim of this framework is not editing because you are just focusing on creating a 3D object from the image. Editing part will come maybe later on, but that once you have the 3D object, can you do anything with that? But I don't know. And I don't, up till now, the paper that I've seen, I've not come across nerves for editing.
Yeah, because I was saying, like for your work, like how are you supposed to, like you're gonna train one, like imagine you're using a nerve, you're using one nerve per like
I will
per.
not be using nerve. This was just to
Okay.
tell that you can actually use a multi-layer perceptron to model
Yeah, but it's the
a
same with the
object.
triplane, right? Like you're gonna have one triplane model per week, like
No,
per brain.
no. So triplanes is you can generate. So each triplane will be for one object, but
Okay.
it's fast enough. Just like you create latent vector for an input image, you
Okay.
can create a latent triplane for an input
Okay.
volume or image or anything. So it's just another latent representation. But over here, there is no concept of latent representation,
Okay.
right?
Okay.
Yeah.
So in processing the triplane, you have um, so you train your model to like for your case, you train your model to reconstruct like a brain.
For my case, I do somewhat like this that I have an MRI scan.
Yeah.
I generate. Uh, I have an MRI scan. I do convolution and I get a 3D volume. Then I do this. I get planes.
Okay.
And once I have the plane, I can sample the point and I can tell that look at this particular point based on the imaging information, give me how much in the template this XYZ coordinate should move.
Okay.
So try to model that. It's quite difficult, actually, it doesn't work that
Yeah.
well, but I'm still working on it.
But you can pass any input you want, like any age, for instance.
Yeah, I can. If you're talking, can I condition this tripling
Yes.
representation? Answer is yes, because uh, I have read papers. Yes, in short, you can constrain, you can condition. Yes.
Yeah.
Yes. I mean, imagine this, right? You can actually condition it using the transformer, or you are using diffusion. You can condition it on the diffusion as well.
But it makes more sense because you have the 3D convolution, so like you actually like extracting some information. You don't have just the coordinates. Like
Yeah.
if you have the coordinates, you don't have any information about the point, like the location in space.
I mean, I have it sort of because I have a template and it is like normalized into the same space. So I know at this XYZ position, I have a point in my ground truth. And I just model that from the template, how much to move, so that it matches my ground truth, sort of like that.
So this one is the best, the most like the best solution for you, like this model.
I wanted to try something fancy actually. That was the primary reason. And it's the results that it is giving on the papers. As I told you, this one is currently state of the art when it comes to 3D model generation. So triplane representation has proven quite powerful. And all of the generation, if you're doing 3D generation, people are using triplanes. So that is why I also try to use triplanes. Yeah, but this one is like I just came across this yesterday. This is 24 ICLR and simple, like cross attention between each of the triplanes. People have been doing convolution in such a way that they can model the relation between these triplanes. He just did transformer. So attention. So yeah, but obviously there is some.
It's not necessarily the triplane that's the problem, it's how you're getting the convoluted shape into the triplane representation. That's the problem.
How am I getting a convoluted shape?
That it's not working for you yet, is potentially because of how you're encoding it into the triplane vector.
Yes, that can be the case. That can be the case. But I actually did this as well, right? That from 3D, and this makes more sense as well to average it out from each of the axes, and I get these triplanes. I did this, but it did not give the best results. So, but I think I'll still do some experiments and maybe it will work. Or maybe the shape is too complicated for this representation. But if you are modeling something simpler, then maybe it makes sense. Or maybe from the brain, if you're modeling something easy, I don't know
It
what.
always comes down, in my opinion, as you know, so wax lyrical about it, because it's just encoding like Euclidean distances and not it's like geometry or topology.
There is no concept of geodesic, or yeah, there is no concept of neighborhood aggregation as well when it comes to triplane representation for 3D. But assumption is, but um, you get some neighborhood information if you make triplanes like this. You just project them. So for each of the point, the neighborhood points from here, they will get aggregated and form one point. So it is sort of encoding neighborhood information, but it's on a not local. It's like from a whole cubical volume. But yeah, but this one, so this is the one that overfits. So at least this generate brain. So so I'm just working to generalize this, but this works. So triplane. So at the end of the day, triplane can model brain, but can it generalize? We'll find out soon. Yeah.
So no, it doesn't make sense, but is there like an equivalent of this triplane but for like frequencies?
So actually, so if your question is multimodal, right? I was thinking that if each of the each of the plane can represent another modality.
Oh, I wasn't thinking of that.
Okay.
But,
Okay. So for frequencies,
like for harmonics, like instead of having
Can you have 4D?
yeah, could you have 4D, but I don't know if that makes sense. Like you have like instead of planes, you have volume.
I mean, technically you do have a volume because this is shown as a plane, but it has channels. Yeah. So it has channels.
So yes, it can work.
Or you had that other example where you modeled like geometry and texture somewhere else. You could have two planes, one that represents temporal and one that represents spatial.
Yeah.
Something.
In fact, I came across a temp. I did not understand that paper yesterday, so that's why I didn't put it. But there is a paper which used triplanes for some temporal modeling. Uh, but yeah, the cool thing, or you can go hierarchical as well. For example, I was thinking maybe if you want to do super resolution, because I think Levi is working on super resolution. So maybe if you go hierarchical triplanes, then you can create 3D volumes of hierarchical, just like hierarchical VQ. You can go hierarchical triplanes. You can model hierarchies of information on a 3D level. So that is also one of the new use cases that can come up. You haven't. Go ahead.
I have ideas, but
Well, go ahead.
no, because like if you model the data on a sphere, right, you can just use two angles to represent the data.
Two angles.
Yeah, two angles like, to parameterize the data on the sphere.
Two typings.
Yeah.
Yeah. But like this is
No, I'm just saying it's like thinking in terms of parameters. Like
okay.
If you have a sphere, we can just like use two angles to parameter.
Okay.
To locate like a point on the sphere.
Yeah.
Okay, so could we have like a triplane with those two parameters, like those two angles, plus a time dimension, and then we can like
basically two of the same, and third plane is temporal.
So then we can simulate it series.
Yes, actually. So, yes. Maybe. I mean, if you normalize the timeline on the grid.
Oh yes.
Yeah, something like that. But yes, people have not investigated temporal thing using this. I don't have a very clear understanding of how this can be used for temporal understanding, but something can be figured out, I think. Yeah. But this is something state of the art, and people are using it everywhere. Yeah.
Does anybody have like, it's like, seems like it's going away from it being interpretable what it's actually doing.
If you want to talk about interpretability, then these triplanes can actually represent projections of the 3D object. So that is the interpretability that people do. And it actually, if you visualize, it can happen that these things that you're seeing is actually the projection of the 3D object. And people have visualized it, it is sort of like that. So that is the only interpretability. But yeah. Oh, exactly 13. Thank you.